Hello, back again. I think you'll notice a few changes here, mostly comments and things that I would typically have something like a header of some sort in front of every file, in the file name and description, probably some copyright information at the top if you're working for a company. This is just a simple example. I want to see how the compiler deals with a for loop. How does it execute a for loop? In C, we can't declare I inside the scope of the for, so it has to be done first. And it is, in particular, this one is initialized to 0. If it weren't initialized, and I tried to compile this, I would get that warning. Uninitialized local variable I is used, so that's good. That warning is coming up. I don't believe it will come up at warning level 3. Just see if that's true. You should always enable as many warnings as you possibly can. It still comes up under 3. But we'll stick with 4. The more warnings, the better. The more chance of catching a bug. So let's see how it works with this. F9, in my case anyway, is a breakpoint. So I'm going to run up to that breakpoint. And for me, Alt-7 disassembles. Now this is a debug build. And remember, subtracting from stack is allocation. Now this is the same as subtracting 4 from a stack, one int worth of space. So this is simply an allocation of 4 bytes. And you'll notice that those 4 bytes are initialized with CC value. And that's typical in a debug build that uninitialized local variables will be initialized with CCs. Now that's immediately being set equal to 0, so we don't have a problem with that. And then it's jumping immediately to BFD, which is here. So now it's moving that variable we just set into CX. These are now 32-bit registers. And comparing that with EBP plus 8. Now remember, everything is times 2 now because we're in 32-bit world. So that would be the same as our BP plus 4, which is the first argument on the stack passed in. So it's comparing this ECX, which we set equal to 0. It has taken from the local variable I, comparing that with argc, and if greater than or equal to, because it's the opposite of less than, then it's going to jump to 444 C19, which is the return 0. Okay. Otherwise, it's taking this same value and putting it now into dx, And into AX goes EBP plus C. Now C is 12. X, remember, plus 8 is the first value, RC. Add 4 more, and that gives you RV, which is our car star star. So that's an EAX. And now, into ECX is AX, which we just set. And you notice that this particular processor has no problem with AX in here. We had problems with AX with the 8086. Obviously, that problem was fixed by the 586, maybe even 486. Also, there's multiply. You can do multiply inside the brackets. So it's taking EAX, the start of this array, adding 4 times DX, which should be an index. Index, yeah, that's I. I is our index. So it's start of array plus 4 times index, which is 0. Pushing that pointer value on the stack and calling this here. Now I think I can put symbols in here. That's the function put s. Then clean up the stack, jump to main plus 14, which is B F4 here. And now with the symbols, it will look a little bit easier. Into AX goes I. 1 is added to EAX. And the whole thing repeats as long as the condition, the comparison of I and argc satisfies I being less than argc. So it's just the same way we would normally have implemented a loop, similar anyway, in assembly. So I didn't supply any arguments. We should get 1. We got the name of the program. This time the condition should fail. Compare ECX with argc. Is it greater than or equal to that? Yes, it is. So XOR. Now this little bit at the end here is always put in. This checks the integrity of the stack before leaving. There's a comparison of EBP and ESP. And in theory, well, here it's adding 4, okay. It's adding back the 4 that we took away, checking to see that we kept our stack clean. If not, it might issue a warning and then return. So there's one thing, there's one example. I'll think of something else, just a minute. Okay, here's something of curiosity I thought of. Not a lot of people like to write this instead of the post increment, presumably thinking that there might be a performance gain. Now let's see if that has any effect on the code. As you can see, it's exactly the same code. There's no advantage to one over the other. In this case, since there's no assignment going on, there's no need for the code to be any different. If an increment is on the right-hand side, that is a post increment, then sometimes a temporary has to be used in order to do an assignment before the increment occurs. But in this case, there's no assignment, so they both compile to the same thing. Okay, we'll try and think of one more thing. Okay, here's something that might be of interest. A character array, let's say. Uninitialized with, well, to make things easy, I'll put it in hex. 100 elements. Let's see how it handles this. Okay. So it's subtracting now. Well, there's 4 we already have, and 100, and there's an extra 10 being subtracted from the stack. And now you'll notice here's one of those rep STOAS. How many reps is that? 46 repetitions. So that must be a quarter of that, I guess. Divide by 2 gives you 80. Divide by 2 again is 40, 46. So these are reps of storing D words into what it's taken now as a D word pointer at position DI. There's that load effective address again. Filling it all up with CCs. Now let's see where I is in fact. I is where it was before, and so the array follows it. The array is further down in memory, so I in fact is the furthest up in memory, just as it appears in the list. Okay. Now, if we initialize this, there's something. If you do this, it should initialize the whole thing to 0. We want our symbols back. I see there's extra space for this stuff. Bounds checking. Now here's the storage of the CCs. And it's using memset in order to set the array to 0. So in one case it's using a rep thing. In this case it's using a memset. I don't know why there's a difference. That's the way it works. Another curiosity might be, well, we don't know the size of the array, but we might have a string here. What does it do in this case? That should give us the length of the string plus 1 to make it easier then. That's 1, 2, 3, 4, 5. We should get 6 elements. Okay. Now the subtraction is less, obviously. into all of these values is going EAX, which is CC. I don't know why. I guess it found that to be efficient enough. Now, I don't know what this business is. It's a D-word pointer. Type descriptor. It's probably easier to see it without the symbol. 4916. We have to see this. Where's that window? Here. Let's see what's at this address. No. This seems like the right. No, it's not. That's 18 different. Just wondering where it gets the string from. Maybe here. So now that'll be a number. Maybe I have to say 0x. Oh yeah. That's the 6f. Pretty big number. So what was this one that we didn't see? It doesn't say hello. This one? There it is. Okay. So that goes into EAX. And then this is an allocation. Let's bring that into 14H value. But it should be copying it. Oh no, it's no, it should copy it definitely. For C2C. That's just the loop again. Looks like it's just copying the pointer. Well, apparently it's just moving the pointer value into this position, -14. Oh yeah, I see it now. I see it now. What this is, it's just the strangest mem copy you've ever seen. EAX is a 4-byte value. 4 bytes of the word hello. And taken from this address. If this is a D word, that spells hello, and that's put into EAX, which is then assigned at C. That's 4 bytes. Now, we're still missing 2 bytes. So we move over to this position. That's where the 6F came from. And a word value was placed from there. That's this position. Which is 6F0 if you write it out byte-wise. And that's placed at the next position. So that's essentially a memcpy. Odd as it may seem, that's memcpy.